Hello. Well, before I begin, I would like to say that I'm really glad I'm here, and I would like to say thanks, Serbi, for granting me the Schmidt, Cern, and Evans Travel Award. So me and Steve have been looking at the magnesium suite samples from Apollo 17. Why have we been doing this? So if you look at this plot that I have here, the summary of ages that we have for most of the highland rocks. In the middle there, you see the magnesium suite rocks. All but three of them are come from Apollo 17 rocks. We can thank uh, Jack Schmidt for this because of the excellent work they did picking up great samples from this site. But it induces a problem or potential problem of bias in our collection of what we know of the magnesium suite. So one of the things that we know about these rocks is that they're very similar, at least the Apollo 17 ones. I'll show you why in a little bit. But what would happen to this plot here if all of the Apollo 17 magnesium suite samples are related to each other? And if that it happens, what would it mean for our understanding of the early moon and its evolution? So if we consider a kind of a regular type of crust magmatism, we would get multiple events with different sources and potentially multiple ages for the formation of a magnesium suite with all of the lithologies that we have distributed all over the crust. Once we get a meteorite impact, the regolith is going to spread that out everywhere. But in the case that we have a mafic layer intrusion, we get all of the lithologies potentially from the same single massive source. And once we get the impact, the regolith will be kind of indistinguishable from the previous case. So what are we doing here? We're comparing most of these rocks. We got a multiple samples from GSC curation team. And we're initially looking at the petrography of these samples. We're looking at petrographical evidence of similarities between textures, mineral abundances, and different things. We're also going then through EPMA mostly to identify the compositions of this mineral and finding like major element trends, some of them which I'm gonna show you now. My talk here, I'm gonna show you here most of the petrography that we've done. We're almost done with all the samples, and we managed to identify multiple petrographical similarities. We also have some very cool compositional trends. And the final step of my work is going to be laser ablation, which Clive Neal has left me very scared of doing now. But we're going to do trace element inversions, like Steve was mentioning in his previous talk, for looking at the parental melts of these rocks, kind of like what the work of Jim Pike did in the late 90s, with more updated partition coefficients and just compare the parental melts of these rocks. So petrographical evidence. One of the most well-known here is just that these rocks tend to have very large grain sizes. You see here a picture of 76535. You can easily get crystals that are 2-3 millimeters long, even bigger than that. And this is actually the first picture I ever saw of the magnesium suite, which just blew me away how beautiful it was. An additional thing that we get here is that most of the faces are compositionally homogeneous. We don't get any kind of zoning mostly in either of these minerals. And they seem to be likely thermally annealed, at least most of them. Another way that we get to study these rocks is by looking at the trap melt pockets. So cumulate rocks tend to crystallize, also trapping little pockets of melt, and the pockets of melt, as the rocks that are getting in the cumulates are getting more evolved, the melt pockets are also getting more evolved. So here we get a melt pocket from 76535, where we can see in the middle, I don't know if I can get here, we get some orthopyroxene in the darker part, and then we get some clinopyroxene and a bunch of chromite. This is how the melt pocket looks like in 7535. But if we go to the norites, then we get a bunch of silica. Oh, sorry, spoilers. We get a bunch of silica, a ton of clinopyroxene also. We get rutiles, and there's a brighter spot there that is actually a niobium-bearing rutile. We also get tiny pieces of melt. This is actually a potassium rhyolitic melt, which leads me to this guy that I have named the shrimp tail. It's half and half. The top half is mostly potassium feldspar integrating with silica, and the bottom half is actually a bunch of clinopyroxene with a little bit of chromite. So we get similarities, especially in the norites. All of these melt pockets are very similar, but we can also see the evolution with the most mafic rocks, how it leads to the evolution of these melt pockets that allows us to compare them. Typical phases that we get here: silica, clinopyroxene, potassium feldspar, meryllites, baddellites, titanium oxides. Another thing that we compare these rocks to is by the appearance of symplectites, especially in the structulites are the most abundant. But symplectites have been associated to a disequilibrium reaction involving olivine plagioclase. And the reason and the explanation that we would get these type of textures in multiple different rocks is because all of these rocks have gone through the similar process of subsolidus recalibration, most likely. And these symplectites are a mixture of orthopyroxene, clinopyroxene, and chromite. And we find them in basically every rock that we've analyzed except the gabbronorite. The dunite has multiple of them. Most of the troctolites also, and even one norite that also keeps a little bit of olivine in it. I've also found some very cool things and that I want to show, especially these exsolution texture in orthopyroxene on sample 72255. It's actually chromite exsolving out of the orthopyroxene, and it's everywhere. And I find it amazing. It really helps here to see that this is not one giant orthopyroxene. It's just multiple orthopyroxenes that have been annealed together. You can see the orientations of them. But the thing is that I haven't been able to find any reference to this type of process, except for an ophiolite in Russia that has some clinopyroxene with the same chromite exsolving texture in it. So it might be a possible indicator that this in fact came from a mafic layer intrusion. We also found this on a troctolite that, and try to follow me here, there's a clinopyroxene minerals in the troctolite that have orthopyroxene lamellae, and the orthopyroxene lamellae in this clinopyroxene also have these chromite solution. So it seems to be an annealing process that is coming on in multiple rocks. And finally, mentioning a little bit of the accessory minerals that we find in here, we get a bunch of titanium oxides, including rutile, niobium-bearing rutile, ilmenite, armalcolite, and I wanted to focus here on a mineral that's called lovringite. It's kind of like an armalcolite, but it also has a bunch of chromium and calcium in it. And the particular thing about this mineral is that we see in both troctolites and norites is that on Earth, at least, this mineral has been exclusively found in just mafic layer intrusions. And it's allowing us to correlate these rocks to this kind of process. So everything at this texture is pointing towards this. So how does the chemistry look in here? Like we get, as many people have shown before, the typical trend of the magnesium suite, starting with the troctolite, which seem to be the most mafic. The dunite is also up there. The norites, we got a grouping there, and gabbronorites that we've been managing to find. At the beginning, we weren't sure which thin sections that we have were actually the gabbronorites, because they seem to be spread out over like polymic breccias. But last week we actually got one of the good governorate class, like the biggest governorate class there is, and we managed to compare to the other three sections, and we in fact have many of them. And compositionally, they plot here, they're pretty far away from the other trend, but still there. And one of the things that we found in this governorates is this insane exsolution texture in this pyroxene. We weren't actually sure what we were looking at here when we found it. I just thought, hey, I'm looking at Jupiter. But we didn't know what this mineral was. Everything else in the sample is mostly pyroxene. So it would make sense that this was pyroxene too, but I've never seen this kind of exsolution texture. But it turns out when you look at it at the SEM, is actually disappointingly boring because it's just pyroxene. But yeah, these kinds of textures are also in the big class of governorite. Not exactly this one, but the rest of them. So this is actually one of the governorite class of the magnesium suite that we're now currently studying. One of the trends that we found as I was going through the EPMA, looking at everything I found basically, and just seemed to notice that the chromite tend to have very varying amounts of titanium in it. So we decided to plot them against the chromium number, and we, thank you. We found this trend that the more data I put into it, the prettier it gets. But this trend indicates that the chromite is, as the rocks are evolving, mostly forming plagioclase, which is increasing the melt in the chromite number by removing the aluminum, and increasing the titanium content, which is mostly incompatible. And the accessory minerals, the chromite, are all following increasing this kind of trend. Relating, in my opinion, like relating the entire suite of rocks that we've been seeing to just one source with that started from a same contents of titanium and increasingly increasing its contents as it's evolving. A particular thing that we also found in the dunite is that there's some chromite with a ton of aluminum in there that don't really match the rest of the things, but we're looking into those right now. It seems to be some sort of symplectite reaction that's different from the typical reaction one. And we're looking at temperatures now. I used to have less samples in this and it looked better because everything seemed to be around 1,000 degrees. And now we have a bigger range. So we're not sure what these actually temperatures are telling us, except for one thing that I noticed that the bigger class, the bigger grain sizes that we get are all at the bottom edge, 76535, 78235, 78255 are the most coarse grained samples. The middle ones are not as coarse, and the one that definitely has the finest grain is 78527, which seems to have the largest, the highest temperature. And that's about the same. We noticed that the Gavros, we know that the Gavros are in equilibrium. I don't know what this particular thermometer is giving us these big uncertainties in it, but it also seems to be correlated to these rocks. And so what follows next? Well, as I mentioned before, we're gonna do the laser ablation, try to invert the compositions, the trace element compositions, and see if the actual parental melts seem to be evolving the same way that we're looking at the petrography. So I'd like to give my thanks especially to the ESC curation team for giving us all of the samples that we've asked for, that we're still getting. So, and to Jacksmith for picking up all of these amazing samples and giving you a little bit spoilers of all the things that I found. Thank you.